Hi, in this video, we want to take a look at hypothesis testing. Hypothesis testing is the structural format that statisticians, scientists, and researchers use data to make conclusions. The goal of hypothesis testing is to have an above reproach framework and method of reaching a conclusion that is as solid as possible. So statisticians have sat down, they've theoretically worked through the mathematics to make hypothesis testing the most solid, airtight method of reaching a conclusion based off of data that you could possibly have. And because of this framework that we've built up, scientists and researchers use it. All right, so hypothesis testing is a statistical method used to make inferences or draw conclusions about a population based on a sample of data. It involves formulating two hypotheses, the null hypothesis and the alternative hypothesis, and testing them using sample data to determine which hypothesis is more likely to be true. All right, so here's an overview of hypothesis testing. First step is to formulate the null and alternative hypotheses. The null hypothesis is the hypothesis of no effect or no difference. This is the default hypothesis. If I don't have enough information, I will go with the null. While the alternative hypothesis is a hypothesis that contradicts the null and represents the claim we are trying to support. These hypotheses are formulated based on the research question or the problem at hand. Next, we need to choose a significance level. The significance level, often denoted by alpha, is the predetermined threshold that determines how much evidence, how strong of evidence is required to reject the null hypothesis. It represents the probability of making a type 1 error, which is rejecting the null hypothesis when the null hypothesis is actually true. Common significance levels are 0.05, 5%, or 0.01, 1%. Next, we select an appropriate test statistic. The choice of the test statistic depends on the nature of the data and the hypothesis being tested. Commonly used test statistics include the t-test, chi-square test, ANOVA, that's analysis of variance, and z-test, among others. Now notice, up to this point, we haven't done anything with data. So at this point, we're talking about what we're going to do with data once I have it. Really, like, why am I going to be checking out my data? Why am I collecting in the first place? Now on this step, we collect and analyze our sample data. Our data is collected through sampling methods, and the sample statistics, mean, proportion, variance, are calculated. The test statistic is then calculated based on the sample data. Next, we determine the critical region. The critical region is the range of values of the test statistic that would lead to rejecting the null hypothesis. It is determined based on the significance level and the sampling distribution of the test statistic. Next, we compare the test statistic to the critical value. And the test statistic is compared with the critical values associated with the chosen significance level. If the test statistic falls within the critical region, the null hypothesis is rejected in favor of the alternative hypothesis. If it falls outside the critical region, then there's not enough evidence to reject the null hypothesis. Next, and this one is, why we are doing this. This step right here is the whole point of all this work, is to interpret the results and draw conclusions. Based on the outcome of the hypothesis test, conclusions are drawn about the population being studied. If the null hypothesis is rejected, it suggests that there is evidence to support the alternative hypothesis. If the null hypothesis is not rejected, it indicates that there is not enough evidence to support the alternative hypothesis. It's important to note that hypothesis testing provides a framework for making statistical inferences, but it does not provide definitive proof. Remember, we have our sampling. There could be a problem with our data. and we wouldn't know about it until it's too late. The results of hypothesis testing are subject to the limitations of sampling variability and the assumptions underlying the statistical tests used. All right, so now let's talk about the hypotheses in hypothesis testing. We have the null hypothesis and the alternative hypothesis. These are competing statements or claims about a population parameter that are formulated based on the research question or problem being investigated. The null hypothesis represents the status quo or the assumption of no effect or no difference. It states that there is no significant change, relationship, or effect in the population being studied. It assumes that all observed differences or effects in the sample data are due to random variation or chance. The null hypothesis is often denoted as either an equal sign, a less than or equal to sign, or with a greater than or equal to sign. And so here, this is the three ways that we typically have null hypotheses presented. You'll notice there's an equal sign in the null hypothesis every single time. We need that for the math to work out, by the way. Depending on the specific hypotheses being tested, for example, if we are testing the mean weight of a population, the null hypothesis might be that the average is 50, assuming that the population average is 50. The alternative hypothesis, H1, also known as the research hypothesis, represents the claim or assertion that contradicts the null hypothesis. It states that there is a significant change, relationship, or effect in the population being studied. The alternative hypothesis is what the researcher seeks evidence for, and it can take several different forms depending on the nature of the research question. And so here are the three ways we present it typically. And you'll notice that we never have equality here. So parameter does not equal value, parameter is greater than value, parameter is less than value. And you'll notice that all three of these are the exact opposite of the three of these. Depending on whether we are testing for a two-sided, two-tailed, or a one-sided, one-tailed alternative, using the previous example, the alternative hypothesis might be that mu does not equal 50, which means that the average is not equal to 50, the population true average. The goal of hypothesis testing is to collect sample data and use statistical methods to evaluate the evidence against a null hypothesis in favor of the alternative hypothesis. The decision to accept or reject the null hypothesis is based on the analysis of the sample data and the calculation of a test statistic, which is then compared to a critical value or p-value to make the conclusion. If the evidence is strong enough, the null hypothesis is rejected in favor of the alternative hypothesis. If the evidence is not strong enough, the null hypothesis is not rejected, and we fail to provide sufficient evidence to support the alternative hypothesis. All right, so you'll notice that the wording I've been using for the conclusions is kind of unusual. And so I want to go over that now. In hypothesis testing, the conclusion of a hypothesis test is typically presented in terms of the null hypothesis and whether it is rejected or not rejected based on the evidence provided by the sample data. The wording of the conclusion depends on the outcome of the hypothesis test and the decision made, of course. If the null hypothesis is rejected, if the evidence provided by the sample data is strong enough to reject the null hypothesis, the conclusion typically states that there is sufficient evidence to support the alternative hypothesis. The wording may vary depending on the specific research question and context, but common phrases used in the conclusion are, we reject the null hypothesis, there is enough evidence to conclude that, the data suggests that. If the null hypothesis is not rejected, if the evidence provided by the sample data is not strong enough to reject the null hypothesis, the conclusion typically states that there is not enough evidence to support the alternative hypothesis. Again, the exact wording may vary, but common phrases used in academic papers are, We fail to reject the null hypothesis. There is insufficient evidence to conclude that. The data does not provide enough support for. It is important to note that the conclusion of a hypothesis test does not provide or does not prove or disprove a hypothesis with absolute certainty. Instead, it assesses the strength of evidence based on the sample data and provides a statistical decision regarding the null hypothesis. Additionally, the conclusion may be interpreted in the context of the specific research question and the assumptions and limitations of the statistical analysis being performed. All right, so if I'm reaching a conclusion, I could make a mistake. We have type 1 errors, we have type 2 errors. In hypothesis testing, a type 1 error, also known as a false positive, occurs when the null hypothesis is incorrectly rejected. The null hypothesis is correct, but we made a mistake, even though it is actually true. In other words, a type 1 error is the incorrect conclusion that there is a significant effect or difference in the population when in reality, there is no such effect or difference. To understand a type 1 error, let's consider an example. Suppose a pharmaceutical company wants to test a new drug's effectiveness in reducing the duration of a specific illness. The null hypothesis would state that the drug has no effect, while the alternative hypothesis would say that the drug does have an effect. If the pharmaceutical company conducts a hypothesis test and rejects the null hypothesis, concluding that the drug is effective, but in reality it's not, they would have made a type 1 error. The company would be making a false positive claim by concluding an effect when none actually exists. The probability of making a type 1 error is directly related to the significance level chosen for the hypothesis test. The significance level represents the maximum tolerance probability of making a type 1 error. Commonly used significance levels are 0.05, 5%, or 0.01, 1%. By choosing a lower significance level, the researcher reduces the probability of making a type 1 error, but increases the risk of making a type 2 error, failing to reject the null when it is false. It is important to control the probability of type 1 errors based on the context of the study and the consequences associated with making such errors. In some fields, such as medical research, when the decisions based on statistical results can have significant implications, maintaining a low type 1 error rate is critical. All right, now let's talk about type 2 errors. And this is going to be very similar to what I just did a moment ago with type 1 errors. In a type 2 error, also known as a false negative, this occurs when the null hypothesis is incorrectly failed to be rejected. The null hypothesis is incorrect. The alternative is correct, but we made a mistake, even though it is actually false. In other words, a type 2 error is the incorrect conclusion that there is no significant effect or difference in the population when in reality, there is such an effect or difference. To understand type 2 errors, let's consider an example. Suppose a pharmaceutical company wants to test a new drug's effectiveness in reducing the duration of a specific illness. The null hypothesis would state that the drug has no effect, while the alternative would state that the drug does have an effect. If the pharmaceutical company concludes a hypothesis test but fails to reject the null hypothesis, concluding that the drug has no effect, when in reality the drug does have an effect, they would have made a type 2 error. The company would be making a false negative claim by failing to reject an effect when it actually exists. The probability of making a type 2 error is influenced by several factors. It's not as straightforward as a type 1 error. And these factors include sample size, variability of the data, and the chosen significance levels, and the magnitude of the effect that we are studying. The type 2 error and type 1 error are inversely related. Reducing the probability of one increases the probability of the other. To decrease the likelihood of a type 2 error, researchers can increase sample size, choose a higher significance level, or use more sensitive statistical tests. However, it is important to strike a balance between controlling type 2 errors and the risk of making a type 1 error. The consequence of type 2 errors depends on the context of the study. In some cases, such as medical research, failing to detect an effect or difference when one exists can have serious implications. Therefore, researchers often perform power calculations to estimate sample size needed to achieve the desired level of power, which is denoted 1 minus beta, where power is the probability of correctly rejecting null hypothesis when it is false, thus minimizing the risk of a type 2 error. All right, so now let's talk about common hypothesis tests. There are tons and tons and tons of hypothesis tests. I'm going to go over the most common ones. So there's the one sample t-test. This is used to determine if the mean of a single sample significantly differs from a hypothesized value. Now, there are assumptions here. I'm not going to read these out. You know, the main thing that I want you to walk away with in this video is the overall rational structure of hypothesis testing. After that, I want you to walk away with knowing if I see this situation, I use this test. All right, so that's the main thing you need to remember. Because if you have a situation, you know which test to use, you can look up that test, you can look up the assumptions, and go from there. I also include R code on most of the tests. So one sample t-test determine if an average is different than some hypothesized value. Two sample t-test, independent sample t-test, compares two means of two independent groups to determine if they are significantly different. And there's two ways to approach this in terms of variance. There's pooled and unpooled. Paired sample t-test. This compares the mean of two related paired samples to determine if they are significantly different. So kind of like a pre and post treatment measurements on the same subject. The next one is the chi-square test for independence. Here we determine if there's an association between two categorical variables in a contingency table. The next one is the chi-square goodness of fit test. These mathematically are the same, but they have different purposes, different derivations. The chi-square goodness of fit test tests whether the observed frequencies of a categorical variable differ significantly from the expected frequencies specified by a hypothesized distribution. Next one is ANOVA, analysis of variance. This tests if the means of two or more groups are significantly different. Now, the two sample t-test that I talked about a moment ago will handle two groups. ANOVA handles two or more. ANOVA can be one way, one independent variable, or factorial, two or more independent variables. Next one is the Mann-Whitney U-test. This is a non-parametric test that compares the medians. Previously, we talked about means, but now we're talking about medians. We compare the medians of two independent groups when the assumption of normality is violated or the data is ordinal. So this is a more flexible version of the t-test. Now, the Wilcoxon signed rank test, this is another non-parametric test that compares the medians of two related or paired samples when the assumptions of normality is violated or when the data is ordinal. Next one is Kruskal-Wallis test. This is the non-parametric version of ANOVA. It's used to compare the medians of two or more independent groups when the assumptions of normality is violated or when the data is ordinal. Spearman's rank correlation test. This is a non-parametric test that measures the strength and direction of the monotonic relationship between two variables. So this is a correlation test. Spearman's correlation is a little bit more flexible than Pearson's. Pearson is straight line. Spearman's is monotonic relationship. Spearman's correlation coefficient tests this test measures the strength and direction of the linear relationship between two continuous variables. So when I say linear, it's a straight line relationship. Next one is the z-test. The z-test really is more of a classic statistics thing. Back in the day, like during the Manhattan Project, the Apollo missions, they used tables instead of calculators. They didn't use R because they weren't around. They had these tables. Watch the movie Significant Figures. They demonstrate these tables. Nowadays, we really don't use the z-test, but it's important if you were stuck on if you were stranded on a desert island and had to do statistics using those old tables, you would be using the z-test. Now, the last test I'm going to talk about is the proportion test, where we test whether the proportion of success or of events in one group differs significantly from the proportion in another group. These are just a few examples of commonly used hypothesis tests. The choice of test depends on the research question, the type of data being analyzed, and the specific assumptions of each test. It's important to note that these assumptions are general guidelines and the specific requirements may vary depending on the variation of the test being used and the specific circumstances of the analysis. Checking the assumptions and considering alternative methods when assumptions are violated is crucial to make valid statistical inferences. All right, so here's the conclusion. Hypothesis testing is a fundamental statistical technique used to draw conclusions about populations based on sample data. It involves formulating two competing hypotheses, the null hypothesis, which assumes no effect or no difference, and the alternative hypothesis, which represents the claim we seek evidence for. The process of hypothesis testing involves collecting sample data, choosing an appropriate statistical test, calculating a test statistic, and comparing it to a critical value or p-value. The conclusion of a hypothesis test is based on the evidence provided by the data and aims to determine whether the null hypothesis should be rejected or not rejected. And so when I make a mistake, there are two possible errors, a type 1 error and a type 2 error. The type 1 error, the null hypothesis is correct but was rejected. In a type 2 error, the alternative is correct, but we failed to reject the null hypothesis. The significance level chosen for the test determines the probability of making a type 1 error, while the power of the test determines the probability of making a type 2 error. That's not 100% correct, but close enough. The conclusions of the hypothesis test are presented in terms of the null hypothesis and whether it is rejected or not rejected. If the evidence is strong enough, the null hypothesis is rejected in favor of the alternative hypothesis, suggesting there is sufficient evidence to support the alternative claim. If the evidence is not strong enough, the null hypothesis is not rejected, and there is insufficient evidence to support the alternative claim. It is important to note that hypothesis testing provides a framework for statistical inference, but it does not provide absolute proof or disproof. The conclusions are based on the observed data and are subject to uncertainty and potential limitations, such as assumptions and sampling variability. Overall, hypothesis testing is a valuable tool for making informed decisions and drawing valid conclusions in various fields, including scientific research, quality control, social sciences, and more. By carefully formulating hypotheses, conducting appropriate tests, and interpreting the results in the context of the research question and assumptions, hypothesis testing helps to provide evidence-based insights for our advance of understanding in the world. All right, well, that's all I've got for you. Life is short. Do math.